Coming up, I build a kitchen and then cook something in that kitchen. So a couple of weeks ago, I put out a call here on LinkedIn asking how architects and interior designers do kitchens in Revit. Surprisingly, I got a big response. You might be wondering, why did I do this? Probably not. You're probably not actually laying awake at night thinking about me. I hope you're not. That would be creepy. Anyway, the story begins back in 2010 in my first architecture job, when I did custom joinery for interior fit-outs. That only went as far as some 1 to 20 2D line work drawings in AutoCAD, which told me nothing about how to actually build casework. Joinery wasn't part of the scope of my work in my other jobs, so I never actually did them in Revit. In 2021, I went looking to buy my first home. For every apartment I inspected, I did a basic layout of my furniture and solar analysis to see which ones were any good. Now, the law advised me not to buy anything built in the era of private certification, so instead I bought a 50-year-old apartment in a great location with fantastic space, light and air, but still mostly in the original condition. But needing to do a full renovation wasn't going to stop me. That was just a design challenge. But by building as much of it myself, I would not only save money, but also learn the hands-on construction skills that an architecture degree or an office job could never teach me. The old kitchen was way too small to store everything, and it would literally crumble into dust when I touched it. I needed to be efficient with this design and milk every last millimetre. I also couldn't use any off-the-shelf units because I only had less than 500 millimeters of depth to work with. I took a look at some publicly available casework families, but quickly concluded that Revit wasn't going to give me the level of precision and flexibility I will need to follow through all the way to manufacture. So I modelled everything up in Rhino where I had full control, storing each module as a block with a letter for its name. The next challenge was how to translate that into physical objects. So I built a grasshopper component for taking the pieces and panelizing them as blocks, inheriting the letter and adding a number. That way I could lay out the pieces on a sheet and send that to a factory with a CNC machine to cut them. They arrived on the back of a truck. I had to sort the pieces, assemble them and install them. I also built the bench out of upcycled jarrah, so no poor tradie had to develop lung problems from cutting fake stone. It's actually a great option. All you need to do is periodically sand it back and oil it up to maintain it. Back to the original question from my post. How much detail do people currently typically build their casework in Revit? Who does the rest and how? Thanks to everyone who responded or even just liked the post to give it a boost on the algorithm. One guy got offended that I used the politically incorrect term LOD. Sorry about that. Big shout out to Jacob Wright from the BIM template, who sent me access to his product sample files. Apart from him, the general consensus seemed to be that the architects either don't know how or don't want to take responsibility for modelling in full detail. It's for the birds! Even when there is a Revit model, they typically only model enough for a rendering and make a set of design intent drawings and send them as a PDF. Then some human in a cabinet factory has to reconstruct that as a model in software like Cabinet Vision, Microvellum or Python. The economics of this seem absolutely crazy to me. Here we are in 2025 and people are still manually going from model to drawing and then back to model again. That cabinet making software is really expensive. And because there aren't that many people who know how to use it, the labour costs are higher than the architect's salaries. So wasn't the whole point of BIM to convey information in a model so that we could reduce the reliance on 2D drawings? Yeah, I know these are still the standard deliverable because regulatory systems require a paper trail, but we are starting to see more projects rely more on 3D models, like this bridge. So how could we vertically integrate this process to minimize the number of shop drawings? Could we even go straight from a Revit BIM model to G-code via Grasshopper and not need any drawings at all? Well, that's what I'm going to show you today. Okay, here we are in Revit land. So if we crack open the one I got off BIMsmith first, you can see There's a couple of parameters, but not very many. Yeah, we can see the way it's been modeled. There's just one U-shaped piece and a top and a bottom and some drawers, and the handles don't really come through. If we compare that to the one Jacob sent, it's got loads of different parameters. You can see even without opening it that there's shelves inside. My only real criticism is that, Jacob being an American, he's modeled it up in arbitrary retarded roller coaster units. And when I've converted that over to metric, I'm getting odd numbers, which is kind of annoying. So with one of these, I just changed it to some whole numbers, and I've built it out of 16 mil instead of 19 because that's what I used on my kitchen. First of our custom components for today. I've got the mum, dad, and little baby rhino icon there. And that's because it's a family. Okay, so select graphical elements, select multiple elements. Grab all these, hit finish. Okay, so it's brought those in. And as you can see, each one is a block. It's brought in the geometry and the reference planes. Let's switch those off. And it's created a separate layer for each type of material. So we crack open one of these, we can see, yep, it's all separate pieces. Whereas if we open the one that came from BIMsmith, that's all one piece. So since most Revit models aren't going to go into that much detail, we can just add it in Rhino side. First up, just draw an extrusion to get the overall size of the box, and run it through this create carcass component. We can bake out the panels to the 16mm white melamine chipboard layer, and the edging to the edging layer. And notice that the panel sizes are a couple of millimeters shorter to account for this edging. Same thing for the drawers, we just make an extrusion. Oh, we've got to put the ortho on. And we pull it back by 13 millimeters, and back by 16 plus 13, 29 millimeters. Now the front face is going to be different. This is set to account for the front face being in any angle and then working out what's the back, what's the sides. And you can switch around the XY plane to choose which one is top bottom and which one is left right. Okay, so we have here our blocks. I switched off all the other layers apart from the white melamine chipboard, and I've renamed them block A and B. Next we're going to pass them through into this custom component here. Next we're going to pass them through here as blocks, which is going to turn them into cabinet objects. This is a special type of custom GUI we've created. This is then going to pass through and be read by this one, which turns it into the panel objects themselves and block definitions. And if we want to visualize these block definitions, we can go over to here and we can create them. So put them on the default layer for now. So each one of those panels has now been flattened. And if we just switch off that layer there, we can see we've automatically got the dimensions and the labeling into each one of these blocks. Now we don't want to actually have to manually lay these out. So what we're going to do is we're going to take out the curves, which is what we're going to need for the cutting anyway. Delete those for now. So that's the curves that we've extracted. And see here how it's in a tree. Those two there are contained within one branch rather than each having a separate branch, because that is the outer and inner curve of this object, which has a hole in it. Next thing we're going to do is create a sheet. So we've got this object here, and we're going to offset it by 20 millimeters inwards so that we don't have the cutting bit get too close to the edge of the material. Now this component here, this can also be used to do multiple offsets, so you can go like that, or you can change whether it goes outward or inward, and you can also join them together. And that would be useful if you were doing a whole filled region which you were trying to cut out in one continuous toolpath. But for now we don't want to join them, we just want one and we want to go inward, and we want to take the first, not the 0th one from that sequence. Now we're going to use open nest. So OpenNest is going to generate the sheets based on that initial outline. It's got a whole bunch of options here. And it's got all of those curves, but it's put them onto 3 different sheets. But it hasn't told us which objects belong on what sheet. So the next component we've created sorts that out for us. So we just want the outer curves here, and we want the inner curves. And that's just the ones from the first sheet in the sequence. They have to be separated because when we get to this node, where we're going to offset, we want to be able to choose what's out and what's in. So you can see here, that's the original curve, and this is the offset. So you can see, say with the one that has the hole in it, we've offset inwards for that inner curve and outwards for that outer curve. Now we need to make these into 3D stacks. So we know our material thickness is 16. We want to go every 4 millimeters down. And we want to cut through the first cut. We're going to go 1 millimeter because that melamine material is a bit harder than the chipboard. And at the bottom we want to go over by 1 millimeter so that we're cutting into that base material underneath to make sure we got a nice clean cut. And we're going to be cutting on the downwards reverse of the Z-axis. So you can see how those curves are going to go down 1, 4,
8.
8's like the number 8.
12, and then 16, 17. So now we've got our stacks, and they're all organized neatly into trees. We're going to pass those through into the generate G-code layer. We're also going to switch on, we're going to get a bounding box. So this is going to take that initial curve that we had and set that as the 0. And we're going to get the centroid of that, and we're going to make that our origin. Likewise, we're going to take this centroid, and then when we generate the G-code, where we have an increment of 1 millimeter, we've set the origin, we have the curves we want to cut. This Z insert, it goes above the sheet material by 1 millimeter each time it changes curve, so that the machine can move the drill bit across without scratching anything. And the bit diameter we want is 6 millimeter bit. So always check with your manufacturer what settings to use on this. I'm going off what I Googled. I haven't actually done this on a full-size sheet material. I've only tested it on a mini CNC, which is the snap maker. Okay, so if we have here the original outlines of the pieces, if we switch on the Viz Path preview, we can see how the machine is going to move itself because it's, a physical 3D circle. It's not an imaginary thin line. We can also visualize the dots, which tell us what the starting point of each curve is in sequence. This kind of looks better in 3D. But it's basically just there to bullshit proof that, yes, indeed, it is actually going to cut what you think it's going to cut. And there is the G-code output for all those pieces. G-code also needs a header and a footer and something for a thumbnail to visualize what's the preview on the screen on the machine itself. So these ones I just took off a SnapMaker, another file that was generated by the SnapMaker software. If you're using a different machine, of course you would want different numbers here. So you've got to check with your manufacturer what their machine is inspecting from other methods of generating files specific to that machine. And then in the end of the day, it's just spliced together as one giant text file. Okay, now let's say we've cut our panels. How are we going to know which one is which? Well, do you remember before how we made these block definitions? And do you remember before how we had these transforms, which were how we oriented the curve from the origin, and we rotated it and we moved it over to where it is on the sheet? If we combine the transforms and the block definitions, and then we bake those as a block instance, they're now in the correct location. So all we would have to do is get a pencil and write B20 onto that piece, and all of the other ones, whatever number. And if we need to be sure, then we can just measure it, and we print this out as a sheet of paper and we cross-check it. For a more high-tech version, you could even, go into carving that number into the panels, but we won't do that for today.
Hello my friends and welcome, my name is Dennis and this is the latest update.
Not from Ukraine, but from Mike's kitchen that he built. Instead of talking about what's happening on the front lines or Trump or airplanes, today we're going to be cooking up a traditional Ukrainian borscht.
Let's go!
Okay, before we decide what to cook, we gotta fry up some garlic and onions. So, put some butter in the pot, chop the onions, add them in, some garlic, some chili, cloves, potato, cabbage, carrot, the main ingredients: beetroot, tomato, capsicum. Mike, don't forget the mushrooms. Thanks, Aaron Patterson. Bit of vinegar, and once it's cooked we can add some sour cream, and there we have it. Traditional Ukrainian borscht. Different to the Russian version, which includes some other ingredients. Fuck off, Sergei Lavrov. So what do you all think? Has this thing got any legs, or am I wasting my time? Is this proof of concept enough to start getting funding that we could build something which could compete with the incumbents? Are architects interested in expanding their scope beyond drawings and all the way up until things start to get physical? They could charge more for it. Or a manufacturer is interested in expanding their scope further back in the design phase. Would they like to learn Rhino and Grasshopper, and then they can start to manufacture things that the traditional software is not designed to do? Let me know in the comments. Thanks for watching, like and subscribe.